So today we have Dr. Tori Borish from now at the Colorado School of Mines, who's going to sort of segue from what Brian just presented into actual physical hardware and setting up those experiments. Take it away, Tori.
Thank you. So I know there have been lots of questions the last several days, and especially the last session, about how do we actually implement this? What is happening physically? So today, hopefully, we're going to get to talk about that. And just hopefully you'll also have a little bit of flexibility, because one of the things about experiments is they don't always work as you would like. And that is something we have been noticing. So I will explain that a little bit later on when you get to actually interact with the experiments. I had to do some kind of last minute changes, so hopefully we'll all just be flexible and go with the flow with me. So I just want to say my two main goals for today. One are to give you the opportunity to actually interact hands-on with some quantum experiments. And then also to help you really reflect on kind of pros and cons and the trade-offs that come with using these types of experiments, to really think about feasibility in your classroom, or if you think these are worth it or not, and for what types of contexts. I have a QR code to my slides that'll show up a couple times later on as well. So just to give you a little bit about my background, my first experimental project was actually right after undergrad, but before I started grad school. I was really lucky to go work on a quantum imaging experiment. So I did that for a year to a year and a half. So that's kind of a subset of quantum sensing, which hasn't been talked about too much, but is still part of quantum technologies. After that, I did an experimental atomic physics PhD, so somewhat similar to what we heard about yesterday from Megan. But the reason I really want to emphasize these two is just to say I do have an experimental background and an optics background. You'll hear later from Justin and Janine, who don't quite have the same background but have still implemented in the classroom. But just the fact that I do have this experience has helped me be able to use experiments with students. So just something for you to think about, like what kind of background do you need or not? After that, I switched and did a physics education postdoc at the University of Colorado Boulder. And there I was actually studying student experiences with these experiments. And this is why I'm here, or that led to me being here today. So I do just want to say that I have worked with students with these experiments, but it has been in the research context. So I have not personally implemented these experiments in a classroom. However, I have talked with a lot of both instructors who have done that and then students who have used these in classes as well. So just I have a slightly different perspective than many of the other presenters who are talking about things they have done in their own classrooms. And just I'm currently at the Colorado School of Mines. I will present some research results, and like all research, this was not done alone. All of these projects I'll be talking about were done with my postdoc advisor, Heather Lewandowski. But I also want to call out a couple of other people. So as you can see, we have these tent cities that you've been hearing about the last couple of days. I would not be able to, fly on the plane with this experimental setup. So I really want to give a big shout out to Justin and Janine. Janine's not here right now, but maybe we could still give them both a big round of applause. As you saw, they have spent hours working on aligning and realigning these experiments so you will be able to use them. So this presentation really could not have happened without their help as well. So I first just want to start, you just did the quantum eraser experiment with simulations. But I want you to spend a couple minutes just chatting with one or two people next to you about these questions. So what is different for students or yourself about interacting with a physical experiment versus simulations or even just thought experiments, right? You could just talk about the quantum eraser experiment in your class. So what is different doing that versus doing the experiment? And what are some ways that you think physical experiments might be able to be particularly helpful in the classroom? So I'm going to give you a minute or two to chat with people sitting near you. Then we can share out these ideas to kind of keep in mind as motivation throughout the rest of this presentation. So go ahead and discuss. All right, so let's all come back together, please. I know you could probably talk about these questions for a long time, but that's what we're going to be doing in the rest of this. Does anyone want to share something they or someone they were talking with, one of the ideas you discussed? Yes, thank you.
Well, we were discussing whether the experiment was, should the simulation come first or should the experiment come first? And I was wondering if you had that discussion when you were organizing the conference. But our thought was, I might appreciate the simulation a lot more after I see the real thing instead of the other way around. The other way around is, oh, I played a game first, and this it'll make the simulation seem less like a game if I see what's happening on the physically or in facing the real world.
That is a very good question. Which should come first, and something I feel like educators are talking about, and I don't necessarily have a good answer for you. I mean, you could ask Justin why he did the order that he did. Personally, I'm very appreciative Brian went first, so he could tell you some of the theory of what's going on, because when you add experiment, you just add all these extra elements too. I could see arguments for both ways. Yeah, maybe one other idea? I heard lots of conversations going on.
So some people at our table talked about how having something physical that you're playing with is more engaging for a lot of students than doing that. And personally, I find that it makes the concepts more real if you can anchor them in, like, here's a concrete example of that quantum phenomenon with, like, photons as a single system. So you can, I always like to build from a precise concrete example rather than a general thing, and I think experiments force you to do that.
Yeah, so a couple ideas here, student engagement, and also just making some of these abstract topics more concrete. I think those are both reasons that a lot of instructors use these that we'll talk about as well. So hopefully you can just kind of keep your ideas in mind as we go through this presentation. So I am going to start presenting a little bit of the research that I've done just to give you a bit of a background, a little bit on how these experiments are currently used in classes. I'm going to try to be brief on that because I know that's probably a bit different than the application you all might have. I want to share some quotes from students just to give you some motivation for some things that some students might be getting out of these. Then you're going to actually have time to work with it may not be a full quantum eraser experiment, but parts of the quantum eraser experiment. And we're going to have kind of an alternate activity as well, so since there are only 4 setups. Then I want to talk about some of the challenges instructors face in using these experiments in their classes, because they're not simple, so I really want to help you see kind of pros and cons. Some of the ideas that students draw on when working with these experiments, because if you have students from all over in many different majors, will they have the background that would be helpful? I think that's a question that comes up a lot in QIS courses. And then kind of synthesizing this all together and comparing experiments with simulations to kind of sum up the last 2 presentations. So starting with the use of these experiments in undergraduate courses, just what experiments am I talking about since you haven't actually worked with them yet? These will be physical versions of the simulations you just did. Here is a photo from my lab in Boulder. So you can see one version and you'll see a slightly different version today. These are quantum optics experiments, so they're usually used to demonstrate single photon phenomena or entanglement. So you can talk about single photon interference. You can do violations of Bell's inequality, which I don't think people have discussed yet so far, but this is a way to kind of demonstrate that you do have entanglement and not some kind of classical correlation. So these are the types of things you can do with these optics experiments. We talked about this a little bit in the last session, but I just wanted to kind of connect with what we had done the last couple days when we talked about computing. Photonic quantum computers do exist. They're not the primary platform, but you can still think about photons as qubits, right? So connecting this abstract math that we've done with something physical. So in the last talk, we talked about photon polarization as a qubit, so a 0 or a 1, whether it's horizontally or vertically polarized. One other type of qubits you use with photons is the path, like physically where this photon is. So we're going to be seeing an interferometer, right? And you could see there's like the top path or the bottom path. You could also define a qubit that way based on where the photon is. And then we also briefly talked about how, or has been talked about earlier, right? Beam splitters can be Hadamard gates. And you can think about all the different optical elements as different gates as well. So we're not going to be focusing on that so much today, but just these are the connections with a lot of what we've talked about the past couple of days. So what are the experiments that people are currently using in undergraduate classes? Here is a list. I guess I just want to point out the second and third ones, a single photon interferometer and quantum eraser. These are the two that we will be doing today. As I said, Bell's inequality violation, entanglement is still this kind of weird thing. And if you want students to get a feel for, like, if you measure over here, you're going to get a correlated measurement over here, you can do that with experiments with the same type of apparatus. There's QKD, and then the last one, this has actually been alluded to a couple times the last couple days. This is a basic quantum computing algorithm. So with 2 qubits, but you can get it in Vantage. So with the same type of setup, there's actually a lot of quantum information stuff that you can do. Most of what has been done so far that I'm aware of is in physics classes, particularly upper division quantum mechanics or advanced lab courses. So this is mostly just to say that the data I have may not be from the same population of students you will be working with, but it's what we have. However, I do know there's at least one introductory physics class that has used these experiments, so I think that could be more similar to potential applications when thinking about quantum information. And when I talked with instructors several years ago, more were thinking about doing it. So I think this may show up in more introductory courses in the near future. And just the way these experiments are used in classes, sometimes they're going to be demonstrations, so it'll kind of be analogous to what we're going to do here, where you get to go, see the setup, maybe take one set of data. But they're also used as many-week projects, so students can learn, say, optical alignment skills, so some skills that are useful for work in the quantum industry as well. And also, this is supported by the Physics Advanced Labs community, and what I mean by that is every year for the past decade, maybe 15 years, there has been a summer workshop teaching instructors how to use these experiments, because I have an hour and a half, and that is not nearly enough to give you all the information you would need if you wanted and had the resources to go and implement these experiments in your classes. But there are some resources available, at least through the Physics Advanced Labs community, which I'm assuming would allow instructors for other departments as well. So just there is community interest and support. So why are instructors doing this? I kind of asked you this at the start. And this first idea goes with kind of what Justin was saying, student engagement. Instructors hope that their students will be excited about these experiments and just motivated to further pursue physics or quantum in whatever way that might be. There's this idea that I'm not going to talk too much about now, but instructors talk about wanting their students to see quantum mechanics, whatever that ends up meaning. And there's this idea, right, that it is really abstract, and you want students to physically see, even though you can't see single photons, or interact with, in some way, actual quantum systems. This can be a way to help students learn concepts. It can be a way to help students learn lab skills, probably less relevant for this audience, but I'll put that up there. And it's also a way to connect this abstract theory that we talk about with experiments. So these are some reasons instructors have for using the experiments. But do students actually accomplish these learning goals? I cannot tell you a definitive answer to this because the studies I have done have been interview studies, so they're all opt-in, and students tend to opt into things when they had better experiences with them. But I do just want to share a few student quotes to maybe help motivate possibilities that these experiments might have. So about conceptual learning, here's a quote from one student. I don't remember which specific experiment, but one of these, they said, "I actually think that even though before the experiment, I would have thought like, yeah, I understand this concept, I feel like I had moments in the experiment where I had somewhat unexpected results, and there was some nuance to the experiment which I didn't know, which led to results that we didn't expect and didn't get us the right results. And because of those nuances, I had to better understand what was happening conceptually on the quantum level to fix those results. That's a conceptual understanding that I don't think I could have gotten by just learning about it. I feel like I had to go through that process of having to solve the problem in the experiment to understand those kinds of things. So I don't know whether or not this would be most common with students who do this experiment, but for at least this one student, they talked about the way that they actually learned new things by working with the experiments. Making this connection between experiment and theory, experiment seems like a natural way to do that. One student was talking about entanglement. They had done Bell's inequality violation, and they said, I think everyone has this kind of sense of what we mean when we say quantum entanglement. It's just fuzzy. But I think this and like the process, the experiment, just kind of fixes it and connects it to the actual physics. So this idea that there are these really abstract concepts we talk about, but what does that really mean? For this student, this was helpful. I've heard other students talk about just having this concrete idea of what is a qubit, that was really helpful for them as well. Or how do you generate entanglement? We're going to talk about that in a few slides as well. And just one other example, quantum mechanics is often talked about as being just math. I have heard students talk about that. There are papers saying students talk about this. But one student, after working through a sequence of experiments, said, and it's making me not ignore things that I ignore to understand the math. Like, you're told that measurements affect the outcome, but then I was like, I mean, you're just saying that. So I'll treat it that way. But it's interesting to see it in action. I can see why someone would think that a wave function exists after this. So for this student, it really helped them connect, like, there's this math and I can follow rules, but what does it actually mean is physically happening in the world? Some students also talked about how quantum wasn't too surprising for them, because evidently students now watch YouTube videos and hear random things about quantum in the world. But it was still good confirmation. So I had some students talk about how these experiments made quantum seem less weird. I will point out some students said experiments made quantum seem more weird as well, so can go either way. Some students talked about it helping them build intuition, and then also this idea of confirming their belief in quantum mechanics. So students said, by the time they get to college, they don't need to see something to believe it, but it still kind of helps. I had several students address this idea, like, I didn't disbelieve it before, so like the weird quantum ideas, but I definitely believe it more now. And then lastly, a couple more of the learning goals. So one, student excitement. Of the 14 students I interviewed, all but one were excited by at least part of the experiments. And that kind of comes from both the concepts and also students just like working with lasers. So one student was talking about Bell's inequality, and they said, it starts off as super buzzwordy, but you're like, this experiment breaks reality and defies our assumptions about the way the world works. And it sounds super cool to start with, and then you find out that that's true. That's not just sort of a sensationalized advertisement. That's actually what we're doing with this experiment, is challenging our assumptions about reality. So students do at least get excited about some of these concepts. And then the one last thing, some of the students identified a connection between the experiments and quantum technologies. Others did not. This may not be too surprising because my research was mostly done with students in quantum or advanced lab courses, where the goals were not related to quantum technologies. I just showed you the list of experiments. There are a lot of potential connections. So I do think that can be, that learning goal probably could be accomplished, but just as an instructor, you probably need to be very intentional about it. All right, so that was kind of the intro I was going to give you just before getting into this specific experiment. Were there any kind of questions at this point, ways these experiments have been used, why you might want to use them, or should we just go ahead and get into the experiment? Great. So I don't need to kind of tell you too much about how this experiment works, because you just played around with it in a simulation. But I do want to talk about some of the differences between a simulation and physical experiments. So as you saw in the last part, you started with the laser, and then you had this entanglement source, which is great. In a simulation, you can just say, I want entangled photons, and they exist. But how does this actually exist in the lab? So we are going to be using some of these Thor Labs kits. So I took some photos from their 150-page manual. But so the way that we do that here is with a laser, and then this nonlinear crystal. So I'm not going to get into the details, but there is a process called spontaneous parametric down conversion, where the idea is that if you send some laser light, in this case it's blue to represent 405 nanometers, so you send it through a nonlinear crystal, and there is some nonlinear interaction where each photon from the pump has some tiny probability of being converted into a pair of entangled photons. So that's denoted by these two red lines. I am using color not to represent polarization, but to represent wavelength, where here energy is conserved. So that's why you go from a higher energy photon to two lower energy photons. And the reason that I drew this as kind of this cone is because you don't end up with two lines of photons going out. You actually have kind of this cone of photons, but you do generate them at either side of the cone. So if you detect a photon over here, you know with certainty, I guess unless it got lost somewhere along the way, that you are going to have its partner photon right here. And these were generated at the same time. So this is what the coincidence counts that you talked about in the simulation, right? You needed the detectors to be the same distance away. That's because these photons were generated at exactly the same time. So this is going to be what we do to get entanglement. Note in the experiments we actually don't have polarization entangled photons. They just kind of have this, well, in energy, and you know that if one's here, the other is over here. But you can do that with a different type of crystal as well. So one other difference, actually, I ended up having to miss a little bit, so I'm not positive if you use this piece, but I thought you were going to use this piece. All right. Yeah. So what I thought there was going to be is one thing you could do if you have an interferometer, you have the two arms. You can make a phase difference between these two arms, and I think you noticed all of the counts may have been at one detector at one point. But if you change the relative phase between the two arms of the interferometer, you can make all of the photons come out the other output of the beam splitter. Sorry, I should have been more prepared for this to disappear. But basically, this is a way that you can kind of change whether you're getting a maximum of interference or a minimum of interference. And the way that this is done in the experiment is just by changing the path length. So we have a mirror, and you can put it on this is called a travel translation stage, but basically it has a knob that you can turn to change the distance by something on the order of microns, so 10 to the -6 meters. But there's also what's called a piezoelectric actuator, which is a piece where you send in a voltage, and that voltage controls kind of how it expands, and can therefore change the distance on the order of nanometers. So by sending in different voltages to this piece, you can vary the length of one of your arms of the interferometer by fractions of a nanometer at a time. And this is actually one of the knobs that we're going to have to control in the experiment. And then one other thing I wanted to mention, I think there was a question earlier on about detectors. I think Brian did actually include a lot of realistic elements of detectors in the simulation, so this isn't something particularly different. But just what we actually have in here are what are called they're avalanche photodiodes. So basically the idea is that you have these potentially single photons. They're hitting this detector. In this case, these are made of silicon. It ends up that photon being incident on the material frees an electron. There's then a voltage that it gets accelerated through, and along the way it ends up freeing a lot of additional electrons. And then those become your regular current that you could measure and get a signal. So these detectors are able to detect single photons. What this means, though, as you can see by all the black enclosures, is that they're very good at detecting light, and there's a lot of light in this room. So you have to be very careful to not hurt the detectors. And you also need to do these experiments in the dark. So, you know, these are some of the potential cons that come along with experiments, is that they're just more complicated. So we are also in this experiment still, oh, yeah.
I have no questions for you because I'm like so excited about this. So I've given the quantum key distribution kit to my students in the cybersecurity class that's like fully online. to take the science fairs, and for for something, as a computer science professor, everything's online. You always give a game, and then the parents go, no more games, they don't. So I was really excited to build this and to share with students, just so they get to see the experiments fail. That doesn't quite work. And I collected feedback, and like you said, I got a lot of amazing feedback. I also got some really bad one, like this did not work. Why did you make me go into campus? And I added the part where they did it in pairs. So I said, like, so you don't suffer on your own, you do it in pairs, and that gives you some networking opportunity. And I also got very good feedback for that. So the paper should be coming out any day now. So I thought it was good, but I also realized, like, I did not make it easy on myself, because I did not know how to troubleshoot any of that, and I didn't know what they were doing. But when I presented, I also like to present it. What's a mirror? Turns out students don't know the mirror. I was like, well, it's really a glass that you coat with something, and you usually coat it with mercury. So you're showing a gold mirror there. That's pretty cool. And then piezoelectric effect, if I understand it properly, it's trying to turn the mechanical energy into voltage.
Well, it turns voltage into a,
Mechanical.
yeah.
Okay, so that was one question I had, because I didn't quite get it there. And then as far as the detector, you keep using words interferometer and interference, and I don't think I'm quite getting what that means. Like, are you just creating noise, or?
Yeah, sorry, I probably should have had a slide just on interferometers. So this is, I think, a good example of something that a lot of physics students might talk about early on in an E&M course, but I would bet that students in most of the other fields that are represented in this room might not have talked too much about. So this is probably some background knowledge that would be really important to give to the students, and I can talk about this right now. So when I'm talking about an interferometer, I'm really talking about, I guess you have something, you separate it, you bring it back together. So in this case, this is what you were working with in virtual quantum optics lab. So you have, say, a laser or a single photon. You have some light that comes into a beam splitter. If this is a laser, you're going to have some of it reflected at the beam splitter, some of it being transmitted. You then have these two mirrors which redirect the light. It then sends it to another beam splitter, where again, the light coming from this direction can get either reflected or transmitted. The light coming from this direction can get reflected or transmitted. So then here, this light is kind of a combination of light that was here and here. So if you were thinking about light as classical waves, you're going to see what's called interference. So what that means is that if you're looking at the amplitude of the wave here, it's going to be larger when these two are in phase with each other. So if you think about kind of sine or cosine waves, if these two are in phase, then it's going to have the amplitude will be higher than it would have been otherwise. But if that's the case, then over here, they're going to be out of phase, and it's going to be destructive interference, so you're not going to see anything. So this is what I was talking about. I thought you were going to have kind of a phase delay used in the interferometer, and what that does is it sets the relative phase of one arm of the interferometer, but not the other. So here you can get that by just moving this mirror a little bit and increasing this path length. And by doing that, you affect kind of where you're getting the maximum interference or the minimum interference. And as you change it, you can see these interference fringes.
So it is like an interference of wave.
Yeah.
It's like when you have a radio and it like makes that funny sound, that's the interference too, right? But wave, like radio, not light.
That's a different interference.
Yeah. I mean,
Should it be more like Kirchhoff's law?
oh, sorry.
Incoming currents.
Sorry, say that again?
Outgoing currents. Is this more similar to Kirchhoff's law for currents? Some of the incomings are equal to some of the outgoing currents?
That is true, but there's also a phase that's important.
Oh.
Yeah, so you should, the amount of light that goes in should be the amount of light.
I mean, because of you probably have diffraction, and because of that, you're also losing some of the amplitudes in other directions as well.
So I think we can ignore, like, there are internal reflections of the beam splitters and stuff probably, and the mirrors lose some. So I think we can kind of ignore that part for now, just think an ideal model, but you're still going to, right? So if you add the light that here plus the light here, that should equal the light that comes in. So that's kind of like Kirchhoff's laws. That is always going to be true, but what you can do by changing the phase on one arm of the interferometer is that you can kind of affect whether more of the light goes over here and less goes over here, and you can make more of the light go over here and less go over here. So you can kind of just change which output the light is going out.
And that's not up to the beam splitter. That is source.
Right, so this is because you have basically the same light here, and if you leave it identical in the two paths, it can interfere with itself.
Oh, okay. So you want to.
Right, so we're assuming these are both 50-50 beam splitters. In reality, you will find they are not perfectly 50-50 beam splitters, but assuming that they are, you are still going to see this interference. Just because you can think of it as like adding two waves that have different phases. Yeah.
The phase difference, it happens inside the splitter, right? That's what you're saying.
No, the phase difference actually just happens by like the light traversing this path, right? If you have a wave, it's going to end up at some point.
So if it's square like this, then there should be no phase difference.
I think just one is like reflected. I think the beam splitter might give a phase to one of the two outputs.
Depends on the convention.
Right, so like there is something happening here. Some of it gets reflected, some of it gets transmitted. You can think about it that way. But when I'm talking about a phase difference, I'm really talking about what happens as the wave is propagating in this arm of the interferometer versus that arm of the interferometer. Yeah, and this is, as I said, a really good point that actually being familiar, I'll talk about later, with classical wave interference was helpful for students when seeing single photon interference. So important to think about what do you need to give your students ahead of time. All right, so to make it also even a little more confusing, this was the interferometer that we used in the simulation. It's kind of nice. You can physically see the two paths that the light might take. I guess I will also say when thinking about photons, if you have a single photon, so a single photon is just a single quanta of light. So you quantize light, the smallest bit you can get. It comes to the beam splitter. This is saying it's basically in a superposition of being in this arm of the interferometer and this arm of the interferometer at the same time. And when it does that, that's when you see interference at the two outputs. So you're still going to get a detector click at one or a detector click at the other. But if you add up all those clicks, then you will see that it's either higher or lower based on the interference pattern. So in the experiment, the Thor Labs kit ends up using a Michelson interferometer. I think this is just because it's easier to align. So you do have a lot of practical limitations that come up when you're using experiments. So this is basically doing the same thing. You just have one beam splitter instead of two. So now these two mirrors, instead of redirecting the light, it just sends it back on itself. So back to the same beam splitter. And then this beam splitter, it's still going to recombine these two paths. But now there's only one output that you could measure because there is some light coming this way as well. But say if you were to put a detector right there, you'd then be blocking the incoming laser. So you're just not able to detect it. So this is just what is going to happen in the experiments that you're seeing. So note it'll look a little bit different than the simulation, but it's basically doing the same type of thing. The one other difference, again, this was, is that in the simulation, you used a half wave plate, so it just rotates any linear polarization into another one. If we get around to the quantum eraser part of this, we're actually going to use polarizers instead. I'm not 100% certain why Thor Labs decided to do that. But it's basically still effectively changing the polarization. It's just attenuating it as well. All right, so this is what the experiment looks like. You will see each of the breadboards has something like this. I'm going to do a quick walkthrough here, and then you'll get to look at it with groups on your own. So we have the laser. It's in this box to control the temperature of it. You turn it on here with both a key and a button. The laser goes through, this is an iris, so just a hole. It can shape the beam. Again, things you need to think about when you are working with an experiment, but not a simulation. It has a couple of mirrors that redirect it. Here is the half wave plate that sets the polarization of it. And that is so that to optimize creation of entangled photons inside the crystal. This is where the nonlinear crystal is going to go. You're not really going to be able to see it because it's really small and the case it's in is pretty big. But this is where you generate the pairs of entangled photons. So you can see that the laser was shown in blue. The photon pairs are shown in red. Note the blue line still exists. There's still only some small fraction of photons in the laser get converted. So you need to block the laser beam, something you need to worry about in real experiments. And then here we have these pairs of entangled photons. So they go to these single photon detectors that have some optics in front of them just to collect as much light as possible. Then, again, you can't see super well in this diagram, but here's a beam splitter. So it's just splitting the light. This is labeled detector T, detector A. This will be detector B. And it sends light into, here's your Michelson interferometer. So this right here is the beam splitter. This is one path that goes and hits a mirror here and then goes back. Here's the other path, and this mirror is on the stage, so you can adjust the position of this mirror. And then afterward, it goes into this detector. One thing to note is that this detector is at a very different path length than these two, but that is where a lot of electronics come in. Not only can you pick your coincidence window, so like what counts as two counts being at the same time, as I think there was a question in the last session about, but you can also set it so that you can have a different path length here that you just give a delay basically to these photons. And then the other part is that you need to run the experiment. So this is what the GUI looks like. These are all the different experiment options that you have. You'll be using it probably set at Michelson. Integration time, it's going to integrate counts over some set amount of time. This is what you're really going to be able to control is the position of the stage. So what you're going to be doing is varying the relative phase between the two arms of the interferometer by varying the position of the stage. And then you're going to measure the coincidence counts. So here you can see it's looking between detector T, so that's one of the photons in the pair, and detector B, which is the other one after it went through the interferometer. So this is what you can see up here. I do just want to briefly point out this G2 measurement. This is a correlation looking at whether you are basically, how many times you're detecting these single photons. So for quantum light, it's going to be below 1 because it should be 0, right? If a photon goes into a beam splitter, it should only be detected at one output or the other. So we're not going to go into the details here, but basically this measurement will verify that you do have single photons or something close to them, and that you're getting particle-like behavior at detection. And here you're seeing these interference fringes, which show the wave-like behavior. So if you put the two of these together, you're seeing both particle-like and wave-like behavior at the same time.
So what was that peak mean?
This peak here? I think if you notice, it kind of corresponds to low counts. So I think it's just noise because there aren't that many counts. This is kind of some product of multiplying the number of counts in the two detectors and dividing by some product of these as well. So I think it's just small counts. You get high denominators.
You're right. You can adjust the integration time so you get more counts, and those spikes come down. If you do it at like 200 milliseconds, you'd see a spike in every node because it's just statistical.
In that 100-some-odd page Thor Labs manual, does it explain like how it actually calculates all this stuff?
Yes. So that is while half of you are working with the experiment, which we're about to do now, the other half of you will have the opportunity to look over some lab guides, student-facing materials. You can look at the Thor Labs manual and look at the theory and the calculations as well.